Welcome, cosmic explorers, to another journey into the profound mysteries that shape our universe. Tonight, we embark on an extraordinary quest to understand the most energetic particles known to existence, the cosmic rays. These invisible messengers, traveling at nearly the speed of light, hold secrets to the universe's most violent and awe-inspiring events. Settle in, find your focus, or let these cosmic whispers guide you to slumber as we unveil the unseen forces that sculpt reality. Before we delve into the depths, consider sharing this journey, liking, or leaving a comment to help more minds venture into the unknown. Let the narration begin. Greetings, curious minds, and welcome to another journey into the vast and often mystifying expanse of our universe. Settle in, find your comfortable space, and allow your thoughts to drift as we delve into one of the most intriguing and yet subtle phenomena that constantly bathes our planet: cosmic rays. Imagine, if you will, the deepest reaches of space. Not the familiar glow of distant stars, nor the intricate dance of galaxies, but a silent, relentless bombardment of nearly invisible particles. These are the cosmic rays, messengers from a universe's most violent and energetic events, whispering tales of creation and destruction, born from stellar explosions, black hole maelstrom, and the colossal collisions of galaxies. For millennia, these particles have streamed through the void, piercing our atmosphere, interacting with our world in ways both profound and subtle, shaping not only the physical landscape around us, but even the very fabric of life. Yet, for much of human history, their presence remained utterly unknown, their existence hidden in plain sight. Today, we stand at a remarkable vantage point. Through ingenuity and relentless scientific pursuit, we have begun to decipher the language of these invisible messengers. This is not astronomy as we typically conceive it, observing light or radio waves. This is something far more primal, a field known as cosmic ray astronomy, where scientists embark on a unique quest to identify and study the potential sources of incredibly high-energy charged particles that emanate from the cosmos. These particles, ranging in energy from merely 1,000,000 electron volts all the way up to an astonishing exoelectron volt, a truly staggering amount of energy for a single particle, are a diverse cosmic menagerie. Primarily, they consist of protons, the nuclei of hydrogen atoms, along with electrons, positrons, and heavier atomic nuclei. The most abundant among these heavier elements is helium, but theoretically, any chemical element forged in the heart of a star or during a supernova can find itself accelerated to these incredible velocities. When we speak of nearly the speed of light, we are not merely using a poetic turn of phrase. Some of these particles, like the legendary "Oh my God" particle discovered decades ago, travel at such extreme fractions of light speed that their journey across interstellar and intergalactic distances takes on an entirely new dimension. These cosmic bullets arrive at Earth carrying invaluable insights into the universe's most energetic processes, acting as direct conduits of information from environments far beyond our direct observation. What makes cosmic ray astronomy truly distinctive, setting it apart from its optical or radio counterparts, is its singular reliance on these charged particles as the primary carriers of information. They are the universe's own particle accelerators, delivering samples directly to our planetary doorstep. But how do we, fragile beings on a small blue planet, detect these ephemeral, high-speed projectiles? It's a testament to human innovation, employing a sophisticated arsenal of detection methods. We use sprawling ground-based observatories that stretch across vast landscapes, high-altitude research balloons that pierce the upper atmosphere, and even artificial satellites that orbit far above our protective atmospheric shield. Consider the ground-based detectors. Vast arrays often spread over hundreds or even thousands of square kilometers. Take, for instance, the Pierre Auger Observatory, an enormous collaborative experiment covering an area equivalent to many small countries, approximately 3,000 square kilometers in Argentina. These detectors don't directly see the cosmic ray particle itself. Instead, they act as vigilant sentinels, waiting for the dramatic aftermath of a cosmic ray's collision with Earth's atmosphere. When one of these ultra-high-energy cosmic rays slams into an air molecule in the upper atmosphere, it initiates a cascade of unimaginable proportions, a chain reaction of particle interactions. This phenomenon is known as an extensive air shower, a deluge of secondary particles, electrons, positrons, photons, muons, and more, collectively showering down through the atmosphere. It's akin to a microscopic cosmic explosion, leaving a detectable footprint across miles of sky and ground. By meticulously analyzing the properties of this air shower, the distribution of these secondary particles, their energies, and their timing, scientists can infer the characteristics of the original, elusive cosmic ray particle. We can deduce its arrival direction, tracing its path back toward its cosmic origin, and estimate its astonishing energy. There are two primary types of ground-based detectors employed in this cosmic detective work. Surface detector arrays, like those at Augur, analyze the air shower at a specific altitude, mapping out the footprint of the descending particles. Then there are air fluorescence detectors, which observe the development of the shower as it propagates through the atmosphere. These detectors capture the faint ultraviolet light emitted when the air shower particles excite nitrogen molecules in the air, essentially watching the shower unfold as a brilliant, if fleeting, cosmic light show. Modern hybrid detectors, such as the aforementioned Pierre Auger Observatory and the impressive Large High-Altitude Air Shower Observatory in Sichuan, China, ingeniously combine the strengths of both these methods, providing a more comprehensive and robust picture of these celestial events. This complementary approach allows for a far more accurate and nuanced understanding of the primary cosmic rays' properties. But our reach extends beyond the Earth's surface. Scientific balloons, like those used in the Cosmic Ray Energetics and Mass Experiment, ascend to the very edge of space, carrying detectors aloft to sample cosmic rays before they are significantly altered by the atmosphere. And in the ultimate frontier, satellites, such as China's Dark Matter Particle Explorer or DAM telescope, directly observe pristine cosmic rays in the vacuum of outer space, offering an unadulterated glimpse into their nature. Why do we expend such tremendous effort, such immense resources, to chase after these nearly invisible particles? The benefits are manifold, illuminating fundamental aspects of our universe that would otherwise remain shrouded in mystery. By carefully studying the energy, direction, and elemental composition of cosmic rays, scientists gain unparalleled insights into the sources and acceleration mechanisms that propel these particles to such incredible velocities. These observations are crucial for unraveling astrophysical processes of staggering power. The violent implosions of supernova explosions, the ravenous accretion disks around black holes, and the intricate, sprawling magnetic fields that weave through galaxies. Cosmic rays are the only direct samples we have from these extreme cosmic engines. Furthermore, the very act of observing cosmic rays has historically reshaped our understanding of the universe at its most fundamental level. Early observations of cosmic rays led directly to the discovery of subatomic particles beyond the familiar trio of the proton, neutron, and electron. The positron, the antimatter counterpart of the electron, and the muon, a heavier, unstable cousin of the electron, were first identified through cosmic ray experiments in the 1930s. These discoveries were foundational, laying the groundwork for the modern field of particle physics and pushing the boundaries of what we understood about the building blocks of matter. Cosmic rays also provide a unique window into the processes of nucleosynthesis, the cosmic alchemy that forges all the elements in the universe. By measuring the composition of cosmic rays, we can infer the conditions and events that led to the origin of the various elements, from the lightest to the heaviest, enriching our understanding of stellar evolution and galactic chemical enrichment. Closer to home, the study of cosmic rays revealed the pervasive presence of magnetic fields and radiation within our own solar system. Some of these high-energy particles originate from far beyond our solar neighborhood, and even beyond our Milky Way galaxy. By analyzing these extrasolar and extragalactic cosmic rays, scientists can estimate the total amount and elemental composition of matter in the vast, intergalactic void, providing crucial information about the overall makeup of the cosmos. These particles are truly extraordinary, generated in environments of unimaginable violence and energy, from exploding stars to the powerful jets emanating from supermassive black holes at the centers of galaxies, to the collisions of galaxies themselves. Cosmic rays offer a rare, direct window into these extreme astrophysical environments, allowing us to probe their physics in ways that electromagnetic radiation simply cannot. But their impact isn't purely confined to grand cosmic scales. Energetic cosmic rays can interact with objects traveling through space, subtly altering their isotopic composition. By meticulously studying these altered isotopes in meteorites that fall to Earth, scientists can unlock astonishing chronological information. They can determine precisely when these meteorites formed and when they subsequently fell onto our planet, providing invaluable insights into the primordial history of our solar system. A cosmic archaeological record written in the very atoms of these ancient space rocks. And astonishingly, the reach of cosmic rays even extends to practical terrestrial applications. Cosmic ray detectors can be utilized to monitor soil moisture for agriculture and irrigation practices, providing real-time data to optimize crop yields and water usage. Perhaps most famously, cosmic rays are fundamental to the process of carbon-14 dating. This invaluable technique allows us to determine the ages of archaeological artifacts and geological formations, revealing the timelines of human history and Earth's dynamic past. Every time a historian or archaeologist dates an ancient settlement or a geologist dates a rock layer, they are, in part, harnessing the power of cosmic rays. The story of cosmic ray astronomy is a captivating chronicle of scientific exploration, marked by pivotal milestones. It began in the early 20th century with the pioneering work of Victor Hess. In 1912, during daring high-altitude balloon flights, Hess definitively discovered cosmic rays, observing that radiation levels increased with altitude, indicating an extraterrestrial origin. This groundbreaking discovery earned him the Nobel Prize in Physics and opened a completely new chapter in our understanding of the universe. The 1930s saw the identification of those new subatomic particles, like the positron and the muon, a direct consequence of cosmic ray studies, expanding our understanding of particle physics and revealing a more complex subatomic world than previously imagined. In a parallel development, Pierre Victor Auger made a profound discovery: the existence of those extensive particle showers resulting from cosmic ray collisions high in the atmosphere, providing the mechanism for how these invisible particles left their giant footprint. The mid-20th century, from the 1940s to the 1950s, witnessed the establishment of the first ground-based detectors, allowing scientists to systematically measure cosmic ray flux and their energy spectrum. This laid the foundation for large-scale experiments, culminating in the establishment of observatories like the Volcano Ranch in the 1960s, initiating a new era of comprehensive cosmic ray research. The 1960s also brought the discovery of cosmic ray anisotropy, the intriguing revelation that cosmic rays do not arrive uniformly from every region of the sky. This unveiled subtle, yet significant variations in their flux and direction, hinting at complex interactions with magnetic fields and non-uniform distribution of their sources across the galaxy. As technology advanced, the 1980s and 1990s saw the emergence of high-energy gamma-ray telescopes. These instruments, while observing gamma rays, were crucial because gamma rays are often produced by cosmic ray interactions near their sources, offering an indirect but powerful means to pinpoint cosmic ray origins. The 2000s ushered in the advent of space-based detectors, exemplified by instruments like AMS-02, the Alpha Magnetic Spectrometer, proudly mounted on the International Space Station. These sophisticated detectors provided unprecedented insights from the pristine environment of space, free from atmospheric interference. And most recently, the 2010s marked significant progress in the exciting field of multi-messenger astronomy. This revolutionary approach integrates observations from cosmic rays with other astrophysical signals, gravitational waves, neutrinos, and various forms of electromagnetic radiation, offering a truly holistic and complete view of cosmic phenomena. It's like assembling all the pieces of a cosmic puzzle to finally see the full, breathtaking picture. Looking toward the future, the field of cosmic ray astronomy is poised for even more transformative discoveries. With continuous advancements in technology and the development of increasingly sensitive detection systems, astronomers anticipate unlocking deeper secrets about the sources, acceleration mechanisms, and propagation of cosmic rays. These insights will undoubtedly contribute to a profounder understanding of the fundamental physics governing the entire cosmos. Upcoming cosmic ray observatories, such as the ambitious Chronicle telescope array, will employ advanced techniques to detect gamma rays, specifically those produced by cosmic ray interactions in Earth's atmosphere. These gamma rays, being electrically neutral, travel in straight lines and point directly back to their cosmic factories. As such, they will represent the most sensitive means to study cosmic rays near their very sources. These next-generation observatories will enable astronomers to study cosmic rays with unprecedented precision, finally allowing us to trace these energetic particles back to their cosmic birthplaces. However, the path forward is not without its formidable challenges. A persistent difficulty in cosmic ray astronomy lies in pinpointing the exact sources of these particles. The problem stems from the very nature of cosmic rays. They are charged particles. As they traverse the vastness of space, they are relentlessly deflected by the ubiquitous magnetic fields that permeate interstellar and intergalactic space. This cosmic game of pinball scatters their trajectories, effectively scrambling their original direction of travel. As a result, tracing the paths of cosmic rays back to their ultimate origins requires incredibly sophisticated modeling techniques and, critically, the integration of multi-messenger observations. Only by combining their signals with those of gamma rays, neutrinos, and gravitational waves can we hope to infer their elusive source locations. Moreover, the extreme high-energy nature of these rays, the inherent need for full-sky exposure to capture these rare events, the imperative to minimize deflection by magnetic fields in our own solar system, and the challenging task of eliminating background noise from distant sources all present significant technical hurdles. Yet, the drive to overcome these challenges is fueled by the immense scientific payoff. The invisible messengers continue their journey, a silent torrent of energy and information from the far reaches of the universe. And as we continue to listen, to detect, and to decipher their ancient cosmic whispers, we inch ever closer to understanding the grand, awe-inspiring symphony of creation itself. Thank you for joining me on this exploration of cosmic rays. Until our next journey, keep looking up and keep wondering. Our journey into the realm of cosmic rays, those enigmatic messengers from the far reaches of the universe, now leads us to the crucial question: how do we actually detect them? These particles, traveling at nearly the speed of light, carrying energies far beyond anything we can replicate on Earth, are not easily captured. They are the unseen, the fleeting, and yet, through human ingenuity, we have devised an array of remarkable tools to hunt them down. Welcome to the intricate world of cosmic ray astronomy, a unique branch of observational science. Unlike traditional astronomy, which relies on light, radio waves, or X-rays, this field uses charged particles themselves, protons, electrons, positrons, and the nuclei of atoms, as the carriers of information. Think of it as listening to the faint whispers of the universe, not through sound waves, but through the very particles that shaped its most violent and magnificent events. The challenge is immense. Cosmic rays span an incredible range of energies, from a mere 1 megaelectron volt to more than 1 billion electron volts. To give you some perspective, the Oh My God particle, an ultra-high-energy cosmic ray detected decades ago, carried kinetic energy equivalent to a baseball thrown at 60 miles an hour, all concentrated within a single subatomic particle. Detecting such an extreme phenomenon, let alone the more common, lower-energy rays, requires a sophisticated and multi-pronged approach. One of the most profound methods for detecting these high-energy cosmic rays is through ground-based observatories. Imagine a vast canvas spread over thousands of square kilometers, dotted with an intricate network of detectors. The Pierre Auger Observatory in Argentina, for instance, spans an area roughly the size of Luxembourg, about 3,000 square kilometers. Why such an enormous spread? Because when an ultra-high-energy cosmic ray slams into Earth's atmosphere, it doesn't just hit a single point. Instead, it triggers an extraordinary cascade of secondary particles, electrons, positrons, photons, muons, and more, a phenomenon we call an extensive air shower. This air shower is like a cosmic fingerprint, expanding as it descends through the atmosphere, showering down to the surface. Ground-based detectors capture these secondary particles. By meticulously analyzing their arrival times, energies, and directions, scientists can reconstruct the properties of the original cosmic ray. It's like being a detective at a massive crime scene, piecing together the events of a collision by examining the scattered debris. There are primarily two types of ground-based detectors that work in concert. Surface detector arrays, as their name suggests, are laid out across the ground, analyzing the air shower once it has reached a specific altitude. They measure the density and timing of the secondary particles that hit the surface. Then there are air fluorescence detectors. These remarkable instruments don't directly catch particles. Instead, they observe the faint ultraviolet light emitted by nitrogen molecules in the atmosphere as they are excited by the passage of the air shower. This light, a telltale glow, allows scientists to actually see the shower as it develops through the atmosphere, providing a crucial, complementary view of its trajectory and energy profile. Modern observatories, like the aforementioned Pierre Auger Observatory and the Large High-Altitude Air Shower Observatory in China's Sichuan province, are often hybrid systems. They combine both surface detectors and air fluorescence detectors. This hybrid approach is incredibly powerful, as it leverages the strengths of each method, cross-referencing data to achieve a far more precise understanding of these elusive particles. It's akin to having multiple witnesses at an event, each providing a slightly different perspective, which when combined, paints a much clearer and more accurate picture. But what about cosmic rays that don't produce these vast air showers, or those we want to catch before they even interact with our atmosphere? For these, we turn our gaze upwards beyond the confines of Earth's protective atmospheric shield. Scientific balloons, like those used in the cosmic ray energetics and mass experiment, ascend to the very edge of space, reaching altitudes where the atmosphere is incredibly thin. Here, they can directly observe primary cosmic rays, undisturbed by the atmospheric interactions that complicate ground-based observations. These balloon-borne instruments are essentially small, specialized telescopes, peering directly into the cosmic stream. Taking it a step further, we launch artificial satellites into orbit. Missions like China's Dark Matter Particle Explorer, or DAMP, carry sophisticated telescopes specifically designed to detect cosmic rays in the pristine vacuum of space. Here, completely unhindered by our atmosphere, these satellites can measure the energy, direction, and composition of cosmic rays with unparalleled precision. They are our eyes and ears in the cosmic torrent, directly sampling the particles before they have a chance to be altered by any earthly influence. The sheer technological marvel behind these detection methods is a testament to human ingenuity and our insatiable desire to understand the universe. But why do we go to such extraordinary lengths? What benefits do these elusive cosmic rays offer us? The insights gained from studying the energy, direction, and composition of cosmic rays are nothing short of revolutionary. They are the keys to unlocking the secrets of the most extreme astrophysical processes in the cosmos. Imagine being able to see the invisible forces at play in supernova explosions, those cataclysmic finales of massive stars. Cosmic rays provide direct evidence of the acceleration mechanisms within these violent events. They reveal the physics of black hole accretion, where matter spirals into the gravitational maw of these cosmic behemoths, emitting torrents of high-energy particles. And they map out the intricate, sprawling magnetic fields that weave their way through galaxies, shaping the very flow of cosmic matter. Beyond the grand cosmic narratives, cosmic ray observations have profoundly impacted our understanding of the fundamental building blocks of matter. It was through the study of cosmic rays that scientists first discovered subatomic particles beyond the familiar proton, neutron, and electron. The positron, the antimatter counterpart of the electron, was found in cosmic ray interactions. The muon, a heavier, unstable cousin of the electron, also made its debut in cosmic ray detectors. These discoveries weren't just academic curiosities. They laid the essential groundwork for modern particle physics, expanding our understanding of the universe at its most fundamental level. Cosmic rays also hold clues to the very origin of the elements. By studying their composition, the types of atomic nuclei they carry, we can unravel the nucleosynthetic processes that forge the elements heavier than hydrogen and helium, those elements that make up planets, and indeed, all life. They tell us about the stellar furnaces where these elements were created and then flung out into the cosmos. Closer to home, cosmic rays have provided invaluable information about our own solar system. Their interactions with the sun's magnetic field and the interplanetary medium have allowed scientists to discover and map the presence of magnetic fields and radiation within our celestial neighborhood. Some cosmic rays, originating from far beyond our solar system or even our galaxy, serve as cosmic probes, allowing us to estimate the amount and composition of matter in the vast interstellar and intergalactic voids, providing crucial pieces to the puzzle of the universe's overall makeup. These energetic particles don't just travel, they interact. When cosmic rays encounter objects traveling through space, such as asteroids or meteorites, they can subtly alter their isotopic composition. By studying these altered isotopes in meteorites that have fallen to Earth, scientists can determine when these space rocks formed and how long they journeyed through the cosmos before reaching our planet. This provides a direct, tangible link to the early history of our solar system, offering insights into its formation and evolution. And the story of cosmic rays isn't just about pure theoretical science. It extends into practical applications that benefit us here on Earth. Consider agriculture. Cosmic ray detectors are now being used to monitor soil moisture, helping farmers optimize irrigation practices and conserve water. And perhaps most famously, the interaction of cosmic rays with our atmosphere produces carbon-14, an unstable isotope that is fundamental to carbon-14 dating. This technique allows archaeologists and geologists to determine the ages of ancient artifacts and geological formations, literally giving us a timeline to the past. The hunt for the unseen messengers has a rich and storied history, a journey filled with serendipitous discoveries and persistent scientific inquiry. It began in the early 20th century with Victor Hess's pioneering balloon flights in 1912. He observed that ionizing radiation increased with altitude, a perplexing finding that led him to conclude that the radiation was coming from outer space, a revolutionary idea at the time. This marked the official discovery of cosmic rays. The 1930s were a golden age for particle physics, driven by cosmic ray research. It was during this decade that the positron and the muon were identified, profoundly expanding our understanding of fundamental particles. Shortly after, Pierre Victor Auger made a groundbreaking discovery. the extensive particle showers that result from cosmic ray collisions high in the atmosphere, validating the idea that these particles were indeed of incredibly high energy. The 1940s and 50s saw the establishment of ground-based detectors, which began to systematically measure cosmic ray flux and energy spectra, building a clearer picture of these enigmatic visitors. The 1960s ushered in large-scale experiments, with the establishment of observatories like Volcano Ranch, specifically designed to study ultra-high-energy cosmic rays. It was also in this decade that scientists discovered cosmic ray anisotropy, the fascinating realization that cosmic rays do not arrive uniformly from every direction in the sky, hinting at their varied origins. As technology advanced, so did our capabilities. The 1980s and 90s saw the emergence of high-energy gamma-ray telescopes, enabling us to observe the gamma rays produced by cosmic ray interactions, providing an indirect but powerful way to study their sources. The new millennium brought space-based detectors like AMS-02 on the International Space Station, offering unprecedented insights from the vantage point of Earth's orbit. And in the 2010s, we entered the era of multi-messenger astronomy, integrating cosmic ray observations with other astrophysical signals, gravitational waves, neutrinos, and light across the electromagnetic spectrum, for a truly holistic and comprehensive view of cosmic phenomena. Looking ahead, the future of cosmic ray astronomy is incredibly exciting. With continuous advancements in technology and the development of even more sensitive detection systems, astronomers anticipate making profound new discoveries about the sources, acceleration mechanisms, and propagation of cosmic rays. These insights promise to deepen our understanding of the fundamental physics governing the cosmos, pushing the boundaries of what we know. Future cosmic ray observatories, such as the proposed Chronicle telescope array, will employ advanced techniques to detect gamma rays produced by cosmic ray interactions in Earth's atmosphere with unprecedented precision. These gamma rays will be the most sensitive means to study cosmic rays near their sources, offering a direct window into the heart of the universe's most violent accelerators. However, the path ahead is not without its challenges. One of the most significant difficulties in cosmic ray astronomy lies in precisely identifying the exact sources of these particles. Because cosmic rays are charged, their paths are deflected by the magnetic fields that permeate space. This means that tracing a cosmic ray back to its origin is not a simple matter of following a straight line. It requires sophisticated modeling techniques and, critically, multi-messenger observations, combining cosmic ray data with observations from other celestial signals to infer their source locations. It's like trying to find the origin of a cannonball that was fired through a complex, invisible magnetic maze. Furthermore, the extremely high-energy nature of some of these rays, coupled with the need for full-sky exposure, minimizing deflection by magnetic fields, and effectively filtering out background noise from distant sources, all present formidable technical hurdles. Yet, it is precisely these challenges that drive innovation, pushing the boundaries of human ingenuity and our ability to unravel the universe's deepest secrets. The hunt for the unseen continues, guided by our insatiable curiosity and the profound desire to understand the whispers of the cosmos. Welcome back to Vibing Science. In our ongoing journey through the subtle but profound realm of cosmic rays, we've laid the groundwork for understanding these invisible messengers. Now, as we delve deeper, we turn our gaze to the most extraordinary events in the universe. Events so cataclysmic, so energetic, that they birth these very particles, sending them hurtling across unimaginable distances. This segment, Echoes of Creation, Unraveling the Universe's Most Extreme Events, is where the invisible becomes a canvas for the most violent and awe-inspiring processes in existence. Cosmic ray astronomy, at its heart, is an observational science. Unlike traditional astronomy that relies on light, radio waves, or X-rays, this unique branch listens to the whispers of charged particles, protons, electrons, positrons, and the nuclei of atoms, all racing through space at velocities so close to the speed of light that time itself almost grinds to a halt for them. These aren't just any particles. They're messengers from the universe's most extreme crucibles, carrying energies that span an immense spectrum, from a modest 1 MeV to an astonishingly high 1 eV. Imagine a single particle carrying the kinetic energy of a well-pitched baseball, but compressed into a speck of matter smaller than an atom. These are the particles that reveal the universe's true power. They are the ultimate cosmic explorers, born from events of unimaginable power. Supernova explosions that outshine entire galaxies, the furious maw of black holes gorging on matter, or the collision of galaxies themselves. Each cosmic ray, in its silent, relentless journey, carries a signature, a faint echo of its violent birth. And it is this echo that we, as scientists, strive to decipher. But how do we catch these elusive travelers? They're not light that can be focused by a telescope, nor gravitational waves that ripple through space-time. They are charged particles, easily swayed by the magnetic fields that permeate the cosmos, blurring their origins. Yet, humanity's ingenuity has found ways to detect these faint signals, to reconstruct their incredible journeys. Our detection methods are as diverse as the particles themselves, spanning from vast arrays spread across the Earth's surface to delicate instruments soaring through the stratosphere on balloons and sophisticated observatories orbiting above our planet. Each method offers a unique window into the cosmic ray enigma. Consider the ground-based detectors, often spanning areas larger than entire cities. The Pierre Auger Observatory in Argentina, for instance, covers an astounding 3,000 square kilometers. These colossal arrays don't directly observe the cosmic rays themselves. Instead, they patiently wait for the aftermath. When an ultra-high-energy cosmic ray, a single, minuscule particle, slams into Earth's upper atmosphere, it triggers an extraordinary chain reaction. It's like a cosmic domino effect. The initial collision creates a cascade, a shower of secondary particles, electrons, positrons, photons, muons, all showering down through the atmosphere in an expansive, luminous burst. This phenomenon is known as an extensive air shower. The ground detectors meticulously measure the properties of these secondary particles, their arrival times, their energies, their distribution across the landscape. From these myriad pieces of information, scientists reverse engineer the event, inferring the original cosmic ray's characteristics, its initial energy, its angle of approach, even its likely composition. It's a colossal forensic investigation, reconstructing an event that occurred billions of years ago and billions of light years away, all from the faint atmospheric footprint it leaves behind. Within these ground-based approaches, there are two primary types. Surface detector arrays analyze the air shower at a fixed altitude, effectively taking a snapshot of the particle rain as it hits the ground. Then there are air fluorescence detectors, which observe the development of the shower as it descends through the atmosphere. These detectors capture the faint ultraviolet light emitted by nitrogen molecules in the air, excited by the passage of the high-energy particles. Imagine capturing the ghost of a particle traversing through the very air we breathe. Modern observatories, like the Pierre Auger Observatory and the Large High-Altitude Air Shower Observatory in Sichuan, China, are hybrid detectors, masterfully combining both surface arrays and fluorescence detectors. This complementary approach provides a far more complete picture, allowing scientists to cross-reference data and dramatically improve the accuracy of their reconstructions. It's like having multiple witnesses at a crime scene, each offering a slightly different perspective, which together paint a more accurate truth. But some cosmic rays never reach the ground, where their energies are too low to create extensive air showers. For these, we send our detectors higher. Scientific balloons, like those used in the cosmic ray energetics and mass experiment, float high in the stratosphere, above much of the obscuring atmosphere. And beyond even that, artificial satellites, such as China's Dark Matter Particle Explorer or DAM telescope, directly sample pure cosmic rays in the vacuum of outer space, untouched by Earth's atmospheric veil. These orbital observatories provide an unadulterated view, crucial for understanding the lower energy end of the cosmic ray spectrum and for detecting particles that might otherwise be absorbed. So, why go to all this extraordinary effort? What secrets do these invisible messengers hold? The benefits of cosmic ray astronomy are vast, spanning across multiple disciplines of science and pushing the boundaries of our understanding of the universe. Firstly, by meticulously studying the energy, direction, and composition of cosmic rays, we can identify the sources and acceleration mechanisms behind these particles. This directly reveals some of the most profound astrophysical processes: the physics of supernova explosions, the powerful jets emanating from black holes, the intricate dynamics of galactic magnetic fields, and even the echoes of primordial processes from the early universe. Each cosmic ray is a tiny data packet, encoded with information about its birthplace. The very existence of cosmic rays has also been a powerful catalyst for discoveries in particle physics. Before the advent of particle accelerators, the natural bombardment of cosmic rays was our only window into high-energy physics. Observations of cosmic rays led directly to the discovery of fundamental subatomic particles beyond the familiar proton, neutron, and electron. The positron, the antimatter counterpart to the electron, was first identified in cosmic ray interactions. So too was the muon, a heavier, unstable cousin of the electron. These discoveries laid the groundwork for modern particle physics, expanding our understanding of the fundamental building blocks of matter and the forces that govern them. Cosmic rays also illuminate the very origin of the elements themselves. They reveal nucleosynthetic processes, the cosmic alchemy that forges heavier elements from lighter ones. By measuring the composition of cosmic rays, the relative abundance of different atomic nuclei, scientists can trace the pathways of element formation within stars and supernovae, painting a richer picture of how the universe created the chemical diversity we see around us, including the very elements that make up our bodies. Furthermore, cosmic rays are sensitive probes of the interstellar and intergalactic medium. Their journeys through space are influenced by magnetic fields and radiation. By studying how cosmic rays are deflected or interact with these fields, scientists discovered the pervasive presence of magnetic fields throughout our solar system and beyond, revealing a more complex and interconnected cosmic environment than previously imagined. Some cosmic rays travel to us from beyond our own galaxy, or even beyond the local group of galaxies. These extragalactic cosmic rays provide invaluable insights into the composition and density of matter in the vast intergalactic voids, offering crucial information about the universe's overall makeup. They are ancient travelers, providing a direct sample of the most energetic regions of the cosmos. Beyond astrophysics and particle physics, cosmic rays even have practical applications closer to home. Energetic cosmic rays can interact with objects traveling through space, altering their isotopic composition. By studying these altered isotopes in meteorites, for example, scientists can determine when these celestial rocks formed and when they fell to Earth, providing precious insights into the history of our solar system. It's a cosmic clock etched into stone. And in a fascinating twist, cosmic rays contribute to processes like carbon-14 dating, a cornerstone technique for determining the ages of archaeological artifacts and geological formations. The interaction of cosmic rays with nitrogen in our atmosphere produces carbon-14, which then gets incorporated into living organisms. When an organism dies, it stops taking in new carbon-14, and the existing carbon-14 decays at a known rate, acting as a natural stopwatch. Even agriculture benefits, with cosmic ray sensors being used to monitor soil moisture, aiding in irrigation practices. It is truly remarkable how something born from a distant supernova can help a farmer determine when to water their crops. The history of cosmic ray astronomy is a captivating saga of scientific curiosity and relentless exploration, dating back over a century. It began with the pioneering work of Victor Hess in 1912, who, during daring balloon flights, discovered a mysterious radiation increasing with altitude, proving its extraterrestrial origin. This groundbreaking discovery earned him the Nobel Prize. The 1930s were a golden age of particle discovery through cosmic rays, leading to the identification of the positron and muon, radically expanding our understanding of fundamental particles. Pierre Victor Auger, in the same era, made another pivotal discovery: the extensive particle showers created when cosmic rays collide with the atmosphere, paving the way for ground-based detection methods. The 1940s and 50s saw the establishment of the first ground-based detectors, meticulously measuring the flux and energy spectrum of these incoming particles. The 1960s marked the era of large-scale experiments with the establishment of observatories like Volcano Ranch and the discovery of cosmic ray anisotropy, the revelation that these particles don't arrive uniformly from all directions, hinting at complex cosmic magnetic fields shaping their paths. The 1980s and 90s saw the rise of high-energy gamma-ray telescopes, enabling us to observe the gamma rays produced when cosmic rays interact with interstellar gas, providing an indirect but powerful probe of cosmic ray sources. And the 2000s ushered in the age of space-based detectors, like the Alpha Magnetic Spectrometer, MS-02, on the International Space Station, offering unprecedented insights from above the atmosphere. Most recently, the 2010s witnessed the emergence of multi-messenger astronomy, a paradigm shift in how we observe the universe. This approach integrates cosmic ray observations with other astrophysical signals, gravitational waves, neutrinos, and various forms of electromagnetic radiation, to create a more complete, holistic view of cosmic phenomena. It's like listening to an orchestra, where each instrument, each form of cosmic messenger, contributes to a grand, unified symphony. As we look to the future, the field of cosmic ray astronomy is poised for even more profound discoveries. Technological advancements and the development of increasingly sensitive detection systems promise to unlock new secrets about the sources, acceleration mechanisms, and propagation of cosmic rays. These insights will undoubtedly deepen our understanding of the fundamental physics governing the cosmos. Future observatories, such as the Cherenkov Telescope Array, represent the cutting edge. These facilities will employ advanced techniques to detect the faint Cherenkov light produced by gamma rays, which themselves are generated by cosmic ray interactions in Earth's atmosphere. Since these gamma rays offer the most direct means to study cosmic rays near their sources, these next-generation observatories will allow astronomers to study cosmic rays with unprecedented precision, probing closer to their fiery birthplaces than ever before. However, despite these exciting prospects, cosmic ray astronomy faces inherent challenges. The primary difficulty lies in identifying the exact sources of cosmic rays. Because these particles are charged, they're profoundly deflected by magnetic fields that permeate space. It's like trying to trace the path of a bullet fired through a strong, unpredictable wind. This magnetic interference scrambles their original direction, making it incredibly difficult to trace them directly back to their point of origin. Unraveling these paths requires sophisticated modeling techniques and, critically, multi-messenger observations, correlating cosmic ray detections with neutrino bursts or gamma-ray flares to pinpoint their elusive sources. Furthermore, the extremely high energies of some cosmic rays, the need for full-sky exposure to catch these rare events, the imperative to minimize deflection by magnetic fields, and the constant battle to eliminate background noise from distant, unrelated sources all present significant technical hurdles. Yet, it is precisely these challenges that drive the relentless innovation in this field, pushing the boundaries of what is scientifically and technologically possible. Cosmic rays are not just particles. They're the ancient storytellers of the universe, carrying tales of unimaginable violence, colossal energy, and the fundamental forces that shape existence. By listening to their silent, relentless journey, we are slowly but surely deciphering the echoes of creation, gaining a profound appreciation for the extreme events that sculpt the cosmos, and in doing so, we are unlocking the deepest secrets of our universe. The journey continues, and the universe, in its infinite wisdom, continues to whisper its secrets to those who are willing to listen. Our journey through the invisible messengers of the cosmos culminates now, as we turn our gaze towards the vast canvas of time, charting the course of cosmic ray astronomy from its humble beginnings to its ambitious future. For over a century, these enigmatic particles have been whispering tales of creation and cataclysm, pushing the boundaries of our understanding and reshaping our perception of the universe. Cosmic ray astronomy, at its core, is a unique branch of observational astronomy. Unlike other fields that rely on light or gravitational waves, we listen to the universe through the charged particles themselves. These cosmic rays, ranging from mere mega-electronvolts to energies that stagger the imagination, even exceeding an exoelectronvolt, like the famed "oh my god" particle, are mostly protons, electrons, positrons, and the nuclei of various atoms. They hurtle through the vacuum of space at nearly the speed of light, carrying with them invaluable insights into the universe's most energetic processes. They're the true speed demons of the cosmos, tiny, yet immensely powerful. The ingenuity with which we detect these cosmic couriers is a testament to human curiosity and scientific innovation. While some might imagine us directly catching these elusive particles, the reality is far more intricate. We employ a diverse arsenal of tools, from sprawling ground-based detectors that stretch for thousands of square kilometers, like the colossal Pierre Auger Observatory, to delicate instruments carried aloft by high-altitude research balloons and sophisticated artificial satellites orbiting above our protective atmosphere. Ground-based detectors, often laid out in vast arrays, operate on a principle of cosmic chain reaction. When an ultra-high-energy cosmic ray smashes into Earth's atmosphere, it triggers a spectacular cascade, a shower of secondary particles, including electrons, positrons, photons, and muons. This extensive air shower then rains down through the atmosphere, painting a transient, invisible masterpiece of particle physics. By meticulously analyzing the properties of these secondary particles, their energy, their spread, their very direction of travel, scientists can meticulously reconstruct the characteristics of the original cosmic ray, almost like forensic scientists piecing together a crime scene from the scattered evidence. There are two primary flavors of these ground-based sleuths. Surface detector arrays, like those at Pierre Auger, analyze the air shower at a single, specific altitude, capturing a snapshot of its development. Air fluorescence detectors, on the other hand, record the entire development of the shower as it descends by observing the faint, almost ethereal glow produced when these high-energy particles interact with nitrogen molecules in the atmosphere. The most advanced observatories, termed hybrid detectors, like the Pierre Auger Observatory in Argentina and the Large High-Altitude Air Shower Observatory in Sichuan, China, ingeniously combine both these techniques, harnessing their complementary strengths to paint a more complete picture of each cosmic ray event. But sometimes, to truly understand the messenger, you must meet it head-on, unadulterated by atmospheric interference. For this, we launch scientific balloons, such as those used in the Cosmic Ray Energetics and Mass Experiment, or deploy satellites like China's Dark Matter Particle Explorer, DAMP. These celestial outposts provide a pristine view of unadulterated cosmic rays at very high altitudes and in the depths of outer space, free from the shrouding veil of Earth's atmosphere. The benefits derived from this relentless pursuit of cosmic rays are profound and far-reaching, touching upon nearly every facet of our cosmic understanding. By diligently studying their energy, their trajectory, and their elemental composition, scientists are not just identifying sources. They are unraveling the very fabric of the universe's most violent and energetic phenomena. We are gaining insight into the explosive deaths of massive stars, the ravenous appetites of black holes, and the intricate dance of galactic magnetic fields that steer these charged particles across vast cosmic distances. Beyond astrophysics, cosmic ray observations have been instrumental in shaping modern particle physics. The keen eyes of cosmic ray researchers led to the groundbreaking discovery of subatomic particles beyond the familiar proton, neutron, and electron. The positron, the electron's antimatter twin, and the muon, a heavier cousin, were first spotted amidst the cosmic downpour, laying crucial groundwork for the standard model of particle physics that governs our current understanding of the subatomic world. These ancient particles also serve as a cosmic chronicle of nucleosynthesis, revealing the processes that forged the elements from the primordial hydrogen and helium of the early universe. By measuring the subtle changes in cosmic rays as they journey through our own solar system, scientists have mapped the presence of magnetic fields and radiation, unveiling the intricate, protective bubble that shields us from the more intense energies of the cosmos. Some cosmic rays originate far beyond the confines of our solar system, even from beyond our own Milky Way galaxy. These intergalactic wanderers allow us to estimate the amount and composition of matter throughout the universe, providing vital clues about its overall makeup and evolution. They are generated in truly extreme environments, exploding stars that outshine entire galaxies, the swirling maelstrom around supermassive black holes, and the chaotic collisions of galaxies. Cosmic rays offer us a rare, direct window into these truly awe-inspiring cosmic events. Even the silent stones of space, the meteorites that occasionally grace our planet, bear the imprint of cosmic rays. Energetic cosmic rays can interact with objects traveling through space, subtly altering their isotopic composition. By meticulously analyzing these isotopes within meteorites, scientists can determine precisely when these celestial fragments formed and when they ultimately fell to Earth, providing invaluable insights into the deep history of our own solar system. But the influence of cosmic rays extends beyond the purely academic, finding surprisingly practical applications in our daily lives. Their interactions with the atmosphere produce carbon-14, an isotope critical for radiocarbon dating, allowing archaeologists and geologists to precisely determine the ages of ancient artifacts and geological formations, revealing secrets of our planet's past. Furthermore, cosmic rays are even being harnessed to monitor soil moisture for agricultural purposes, helping farmers optimize irrigation practices and conserve precious water resources. The story of cosmic ray astronomy is a fascinating tapestry woven over more than a century, marked by a series of monumental discoveries. It all began in 1912 with the pioneering balloon flights of Victor Hess, who, defying the dangers of high altitudes, unequivocally discovered the existence of these penetrating radiations from outer space. This singular act of scientific courage earned him a Nobel Prize and sparked a revolution in physics. The 1930s saw a flurry of breakthroughs, with the identification of new subatomic particles like the positron and the muon, dramatically expanding our understanding of the fundamental building blocks of matter. In parallel, Pierre Victor Auger, another towering figure in the field, discovered the existence of extensive particle showers triggered by cosmic ray collisions high in the atmosphere, laying the groundwork for the ground-based detection methods we use today. The mid-20th century, the 1940s and 50s, witnessed the establishment of the first ground-based detectors, meticulously measuring the cosmic ray flux and their energy spectrum, providing the first comprehensive maps of these celestial messengers. The 1960s marked a significant leap with the establishment of the Volcano Ranch Cosmic Ray Observatory, initiating large-scale experiments that pushed the boundaries of detection capabilities. It was also during this decade that the discovery of cosmic ray anisotropy emerged, the startling realization that these particles do not arrive uniformly from every region of the sky, unveiling subtle variations in their flux and direction, hinting at the intricate magnetic landscape of the universe. The 1980s and 90s heralded the emergence of high-energy gamma-ray telescopes, enabling observations of gamma rays produced by cosmic ray interactions opening a new window onto the energetic processes that birth these particles. The 2000s brought us the advent of space-based detectors like AMS-02 on the International Space Station, providing an unprecedented view of cosmic rays from the vantage point of space, unburdened by Earth's atmosphere. And in the 2010s, we entered the exciting era of multi-messenger astronomy, where cosmic ray observations are no longer solitary endeavors, but are integrated with other astrophysical signals, gravitational waves, neutrinos, and electromagnetic radiation, for a truly comprehensive and holistic view of cosmic phenomena. This synergistic approach promises to unlock secrets that were previously beyond our reach. As we look towards the horizon, the future of cosmic ray astronomy burns brightly, filled with immense promise and exciting challenges. With relentless advancements in technology and the development of ever more sensitive detection systems, astronomers anticipate a new wave of profound discoveries about the enigmatic sources, the powerful acceleration mechanisms, and the intricate propagation of cosmic rays throughout the cosmos. These insights are not just academic. They will contribute to a deeper understanding of the underlying physics that governs the universe itself, from the smallest quantum fluctuation to the grandest cosmic structures. Future cosmic ray observatories, such as the ambitious Cherenkov Telescope Array, will employ advanced techniques to detect gamma rays, those powerful secondary messengers produced by cosmic ray interactions in Earth's atmosphere. Since these gamma rays offer the most sensitive means to study cosmic rays near their very sources, these observatories will enable astronomers to peer into the hearts of cosmic accelerators with unprecedented precision, almost like deciphering the DNA of a distant supernova. However, the path ahead is not without its hurdles. Cosmic ray astronomy grapples with a fundamental difficulty: identifying the exact sources of these high-energy particles. Because cosmic rays are charged, they are constantly deflected and steered by the pervasive magnetic fields that permeate space. This cosmic dance effectively scrambles their original trajectories, making it incredibly challenging to trace their paths back to their origins. Reconstructing their journey requires sophisticated modeling techniques and, critically, the powerful synergy of multi-messenger observations to infer their true source locations. Moreover, the very nature of these incredibly energetic rays presents technical challenges. Achieving full-sky exposure, minimizing the deflection by those pervasive magnetic fields, and effectively eliminating background noise from distant, unrelated sources all demand ingenuity and technological prowess. Yet, these very challenges fuel our drive, pushing the boundaries of what is possible as we continue our quest to decipher the invisible messages that have been traveling across the vast cosmic ocean for eons, whispering the grand story of our universe. The cosmic chronicle continues, and with every detected particle, with every new observatory, we come a step closer to understanding the universe, one invisible messenger at a time. And so, our journey through the realm of cosmic rays draws to a close, but the universe's grand narrative continues to unfold. We've traced the paths of these enigmatic particles, from their violent births to their silent arrival on Earth, uncovering the profound insights they offer into creation itself. If this exploration has resonated with you, I invite you to share your thoughts in the comments below, like this video, and subscribe to join our growing community of curious minds. What cosmic mysteries or scientific wonders would you like to explore next? Until our next deep dive into the unknown, keep looking up and keep vibing with science.